All right, you don't need to see my mug in the corner. Now, one of your classmates asked me if I could record these in 1080 pixels, and so hopefully you'll be able to see these physics interactive simulations a little better. Let's start with a basic one here. Yeah, no, I want to start with this one. No, I don't want to start with that one either. Oh yeah, yeah, that was good. All right, so here's the battery. All right, so here's the desired voltage. All right, so let's flip the battery over. If I go this way, see, once I get past 0 voltage, let's go to the right. Now look what happens. These little chemicals go over and grab the electrons, put them here. Even though they're trying to get here to the positive side, they put them over here. And if we put in a wire, then they'll run all the way around. Okay, and that's what this looks like, I think. Yeah, here we go. Here's a little bit better view of what's going on. And here's the resistance inside the wire, right? And it's getting hot, cold, whatever. So now, watch what happens when I decrease the resistance. Watch what happens to the temperature in the wire when I decrease the resistance. Look at this cold thing down here. It's getting hotter and hotter and hotter. If I decrease it anymore, it gets really hot. And if I increase the voltage while I'm doing that, I'm going to start a fire. Low resistance makes that wire get very, very hot. Okay, where we want the heat to be dissipating from is from any kind of machine or light bulb or something. If you don't believe me, touch the light bulb. Now the reason the light bulb has such a high resistance, it's got a very low resistance, but then the resistance goes way high because it gets hot. And so the current stays kind of the same through it. And that was Edison's biggest problem in trying to figure out how to get this incandescent light to work. And then once he figured out that problem, it was kind of cool because we didn't kill whales anymore. We decimated the humpback whale and baleen whale population in our oceans because whale oil burned for a long time, and all those street lamps and everything else was burning off whale oil. Once we figured this out, the incandescent bulb, we stopped killing whales. But then what did we start doing? We started digging coal, and ta-da, that's what we got. So here's another thing. Look at the last thing we talked about in the last. So this is a circuit, all right? So let's increase the resistance a little bit more. Let's get this to calm down a little bit. Increase the resistance. Now it's getting a little cooler. So I've increased the resistance and I've lowered the voltage. So therefore the amperage is getting really small. Current's not flowing very fast. All right. And then last but not least, here's where we kind of ended yesterday. All right, so we've got the resistance. Notice P is equal to L over A. This is the resistivity of this piece of material here. I'm not sure what it is. It's 0.46 centimeters. Okay, they just left it at 0.46 amps centimeters. I don't really know what that material is. It's not a very good conductor of electricity. That's for darn sure, because this is so high. I mean, this is 10 to the negative 2 meters, ohm meters, which is what and most things we saw like wires and things like that, copper wires, silver wires, were at 10 to the negative 8 good conductors. But anyway, but we can still see. So if we increase the length, the resistance gets big. Decrease the length, the resistance gets small. Again, small resistance in that wire can make things get hot and melt things. So if you got a short little extension cord on a big fat on a big fat wire, you got very low resistance. That's not good. You're going to need to get a longer wire. Little skinny wire, long thing, you got good resistance in there. All right. Okay. There we go. So we got through that. So now let's look at the slides. Where were we? Here's where we were. Of course, it didn't keep what I had on there before. All right. What does this say? "16-gauge cord should be used for longer distances." Now, 16-gauge cords is thicker because fewer of those cords can fit through a certain circular area. It's kind of like the spaghetti servers. Have you ever seen those little spoon-like things with holes in them, going from a big hole to a little hole, where you know how many pieces of spaghetti you can get through that little hole. All right. Anyway, resistance and resistivity. Resistance goes up if something gets hot. All right. Resistance goes up if something gets hot. And so here is our temperature coefficient of resistivity. Okay. And it directly correlates to the resistance. So if you had the original resistance, change in temperature, as long as we keep the same area and the same length and all of that, we can use this formula here, because all that stuff cancels out for the resistance if those are all kept the same. Okay, the only thing that's going to change, notice we can get a higher resistivity here, which will decrease the resistance, right? And so here we're going to get a higher resistivity, or lower if it gets colder. The resistance goes down. And so actually, if you get all the way down to, like, let me show you. If we're going to take, if we are going to take this down to, like, the temperature, the change in temperature is down around 4 kelvins. Okay? Temperature's down around 4 kelvin. That is very, very cold. Okay? That's extremely, extremely cold. But we use this in centigrade. So that would be like minus 269 degrees centigrade. So our R would equal R naught of the resistor of that material plus that alpha of whatever that material, which is another chart that we use, times negative 269 changing kelvins there. This gets 1 plus that subtracted. That makes R really, really small. And this is what is known as a superconductor. We don't need, once we get those electrons moving in a superconductor, we don't need any more battery attached or any other power supplies attached. It'll just keep going by itself. That's superconducting materials. The problem is they have to operate at really, really cold temperatures. Now they're looking at, over the past 10 or 12 years, they've discovered other materials. They've built other materials that do, that they call high temperature. Well, the high temperature is like around liquid oxygen type temperature, like minus 169, minus 170, liquid nitrogen temperature, or down around 80 or 90 kelvins. All right. Well, anyway, so there's a little background there for you. And then we talked about electric power. I don't know if I did that or not. So I'm going to stop here, and then we'll just kind of jump into the slideshow here. All right.